Hello everyone, welcome to the channel. Have you ever wondered what actually happens when we take a smooth continuous audio signal, chop it up into digital numbers and then try to glue it back together? Today we are getting hands-on with experiment 3, sampling, aliasing and reconstruction. We are going to push a signal to its absolute limits and look at the actual graphs to see what happens when we sample above, exactly at and below the famous Nyquist rate. Let's pull up our first graph. What you are looking at here is our original perfect continuous signal. Notice how it has a slow rolling wave with a faster jittery wave riding on top of it. That's because it's a two-tone waveform xt equal to sine 2 pi ft plus 0.5 sine 2 pi f2t. The big slow wave is our f1 at 5.0 Hz with an amplitude of 1.0. The first wiggles are our f2 at 22.0 Hz with a smaller amplitude of 0.5. Because our highest frequency is 22.0 Hz, the Nyquist theorem tells us our speed limit for sampling the Nyquist rate is exactly double that, which is 44.0 Hz. We are going to rebuild this signal using a realistic truncated sync interpolator. Let's take the case A above the Nyquist rate. First up, case A. Here we are sampling really fast 220.0 Hz, which is way above our 44.0 Hz Nyquist requirement. The time graph, look at the dots on this first plot. These dots are our digital sample. Notice how closely they trace that original smooth line. There are 880 sample over our 4.0 second record, leaving almost no gaps. Now let us move on to the FFT graph. Now look at the frequency spectrum below it. You clearly see two sharp spikes, one at 5.0 Hz and another one at 22.0 Hz. When we reconstruct this, the new line perfectly shadows the original. In fact, the error graph is practically flat, showing a tiny RMAC of just 0.008676, which only happens because our sync window isn't infinitely long. Now let us move on to the case B, exactly at Nyquist rate. Alright, now things gets weird. Case B is our critical case. Textbooks say sampling exactly at the Nyquist rate is the absolute bare minimum, but let's see what happens on the screen. The time graph look at where our rate sample dot landed for the slow 5.0 Hz wave. We still have a shape, but for the first 22.0 Hz wave, the dots are landing exactly on the zero crossing, the middle line. Because sin pi n equal to 0, for every sample, we completely miss the peaks and valleys. And if we check out the FFT plot now, the 22.0 Hz spike is just gone. It vanished. Only the 5.0 Hz spike survives. This graph perfectly shows why you cannot just sample at the strict Nyquist limit in the real world. If your timing is even slightly off, you literally erase the data. Now let us move on to the case 3, case C, below the Nyquist rate. Finally, case C. Here we get lazy and sample at just 30.0 Hz, which is way below our 44.0 Hz requirement. This creates a phenomenon called aliasing. The frequency FFT graph is closely at the spectrum. We still have our 5.0 Hz spike. But where is the 22.0 Hz spike? It's gone. Instead, there's a strange new phantom spike right here at exactly 8.0 Hz. Why 8.0 Hz? The math explains the graph. F aliasing equal to mod of f minus k fs. If we plug in our numbers, we get exactly 8.0 Hz. The high frequency folded back into the low frequencies. The time graph, we look at the reconstructed wave. The red line completely misses the first wiggles of the original blue line. Instead, it draws a slow, smooth 8.0 Hz wave that never actually existed in our original signal. The computer has literally hallucinated a frequency because we didn't give it enough sample. And there you have it. The graph shows us exactly how the math predicts. To get this super clean visual result, we actually used two separate time grids, one to simulate the real hardware capturing the dots, and a super dense render grid just to draw these smooth lines and calculate our errors accurately. The visual proof is right there on the plot. Always give yourself plenty of headroom and sample comfortably above the Nyquist rate. Also, before I forget, if you want to run these exact same tests yourself, I uploaded all the Python code, the raw data, and the graphs we looked at today to my GitHub. The link is right down there in the description. So go pull the repo and play around with the sample rates. If seeing this graph helped the concept click for you, hit that like button, subscribe for more signal processing deep dives. Catch you in the next one. Thank you.